morning, everybody. So my name is Konstantin, and I will continue this mitochondrial genomic topic, and I will concentrate only on mutagenesis. So I will not touch selection. I will try to avoid it because my goal is to understand rules of mutagenesis. And because I am not able to finish in 15 minutes, I will start with my take-home messages. So first, that I will try to convince you that mitochondrial mutational spectrum is associated with level aerobic metabolism, probably through oxidative damage. And for you, maybe it looks trivial because everybody says that there are many oxidative damage compounds in mitochondria, but on DNA level, it was unknown till recent moment. So everybody was looking for oxidative damage, which works in nuclear genome, but in mitochondria it's different. So it was a big puzzle in the scientific community. And the second topic, that majority of amino-acid substitutions, they can also follow this mutational bias. And so here I will question that maybe purifying selection is not as strong as everybody believes in case of mitochondrial genome. Okay, let's go. I will remind you a little bit about mitochondrial replication. So first, this is circle, that's mitochondrial genome. So there are several mitochondrial genomes in each organelle, and there are hundreds or thousands of mitochondrial genomes per cell. And important to remind that this replication is asymmetrical. So it starts here, origin of heavy replication, it goes down to origin of light chain replication, and during this moment, parental heavy strand, this one, is single-stranded, so it's naked, more or less naked. So this state is very prone to accumulate mutations. And majority of mutations, transitions, such as A to G and C to T, they occur on this heavy strand. That's why we use this H symbol. So it means that mutations originate on heavy strand. Okay, and so having this information, we can just collect all mutual mutations in mitochondrial genome. So neutral, for example, synonymous, rare, etc. And we just put them together and we say, so all mutations, they look like this. So here you see 12 bins. So all possible combinations of mutations from, for example, from this one is from C to T, this one from A to G on heavy strand, and majority of other mutations, they are rare enough. So two of the most common, C to T and A to G. And it goes in line with this idea that majority of mutations are coming when mitochondrial DNA is single-stranded. Okay, and as I mentioned before, that if we try to use knowledge of mutational spectrum, mutational signature from nuclear genome, it doesn't work. For example, if we analyze mitochondrial somatic mutations in human cancers, and we take, for example, melanoma cancers, we expect that UV light will mutate mitochondrial genome. We expect to see mutational signature of UV light, but we don't see. The same with, for example, lung cancer. So if we analyze somatic mitochondrial mutation from lung cancer of tobacco smokers, we know that tobacco smoke leads to specific mutations in nuclear genome, but we don't see these mutations in mitochondria. So mitochondria is unusual. And the same was with oxidative damage. So the typical mutation of oxidative damage in nuclear genome is transversion from G to T. And in mitochondria, it's like 1%. So G to T, if I can find it, so it's a gray little bin here, so it's very, very rare. So it doesn't work. And we decided maybe we just need to find new rules. We should not just use a nuclear genome as our like vocabulary, but we can just derive de novo mutational signatures in mitochondrial genome using evolutionary approach. So maybe we should not start with cancer, we start with evolution. And what we did, we analyzed mitochondrial mutational spectrum for hundreds of mammalian species, and we observed that generation length, so this is short-lived mammal, and this is long-lived mammals. So generation lengths perfectly explain difference in rules of mutagenesis of mitochondrial genome. And the main difference is in this mutation A to G, this blue bin. So A to G is rare enough, so we draw this red gradient. So it accumulates along the major arc slowly in case of short-lived mammals, and it accumulates fast enough in case of long-lived mammals. So our working hypothesis is that A to G is a hallmark of oxidative damage on single-stranded DNA on this major arc when it is single-stranded. And for now, I mean, if you're interested in details, just read this recent paper. And now we just extend this observation because oxidative damage can be not just the result of aging, but it can be a result of temperature. And please come to Alia, to her professor, and so she will explain that fishes, for example, which inhabit warm water inhabitants and cold water, they have different metabolism, and because of different metabolism, they have different mitochondrial mutational spectrum. Or ask Clara, and she will explain the different nematode species, different life history traits. They have also different mitochondrial mutational spectrum. Or visit Bogdan Foster, and he will explain that having information about evolution, we can come back to cancers and compare glioblastoma, melanoma, basal cell carcinoma, and now we understand that they behave differently because we know that we are looking for this A to G mutation, which is hallmark of oxidative damage. Okay. Till now, I discussed 12 mutations. So from A to G, from A to T, from A to C, etc. But now, if we take into account neighbor nucleotides, so 4 before, 4 after, instead of 12, we will have 192. And so recently, we just combined all polymorphism from all vertebrate species. So here we use 200,000 mutations, more than 1,000 species, to get this very detailed mitochondrial mutation spectrum. So this is the most detailed spectrum. Even for cancer, we don't have so detailed mutagenesis of mitochondrial genome. And now we can analyze different peaks. For example, this one, it's C to T in the context C before and C after. And we just Google and we find papers that, okay, this is experimentally validated how oxidative damage of single-stranded DNA. Exactly this transition, CCC to CDC. And we can analyze, for example, this unusual pattern, like stairs, G to A, and we go to special data sets and we see it looks like deficient basic excision repair. And we can analyze A to G, green one, again compare with with the cancer data set, and we say it looks like methylation of adenosine, which was recently described for mitochondrial genome. And this methylation of adenosine is really typical for mitochondrial genome and for prokaryotic genomes. It's also a result of stressful conditions, etc. So C to G behave as if a basic site here. So having this information, we can just use huge knowledge from cancer field to try to deconvolute observed mutational spectrum to different mutagens, to different rules, to understand better mutagenesis of mitochondrial genome. Okay, and so please come to this poster of Dima, and he will explain details of this 192 component mutation spectrum. So now, if we can use this information, so we can take our data, empirical data from our observed mutation spectrum, and we can deconvolute. We can say in this sample, 20% oxidative damage, 5% methylation of adenosine, etc. Yes, we can try to do it. And please visit the poster of Maxim, and he will try to explain how we can use mitochondrial component of human fertility and infertility, how we can deconvolute embryos, human embryos, which can be recommended for transfer and not recommended. Posters Ivan and Masha, where they describe mitochondrial accumulation of mutations with aging, and again Bogdan, so counted his poster 2 times. Now, take home message 1. Mitochondrial mutation spectrum is not constrained as it was considered before. It's informative. So the little variation between tissues, the little variation between species, they can inform us about level of aerobic metabolism. And because it's pure bioinformatics, I don't have nice photo or video, so I can't show you interesting slides. So we decided to draw our results. So please enjoy. This is our mutation A to G. So A to G is a hallmark of oxidative damage. And this is also mutation A to G. This is mitochondrial clock of aging. And this is a lot of A, and this is G, and this is mitochondrial hemisphere of life. And this is also A to G. And you can ask me during coffee break what does it mean.
I can tell you.
And also A and G.
It's 8 times growth.
Yeah. Okay. So now a second part. Till now I presented that nucleotides can mutate and they can inform us about different mutagens. Okay. Now this is if you forgot mutation, it's A to G, the most important. And now we can extend logic and we can say what would happen if selection is very poor, is very low. Okay, we just assume that there are two mutations, C to T, red, and A to G, and this is mitochondrial genetic table, genetic code. And we say, let's imagine we have Q to G, no selection. So, first we need to make our mutations, we go to reverse complement. So instead of A to G, it will be T to C on the light chain because light chain is identical to mRNA, so we need to do this conversion. And now our two mutations, T to C and G to A. And for example, what will happen? So first T, second T here would mutate to C. So phenylalanine will mutate to serine. Okay, now serine, first T, will mutate to first C. So serine would mutate to proline, etc. So we have many trajectories like this, and they are driven by mutational spectra. And we draw this butterfly scan, and we say we can test it because we have expected gainers, proline, histidine, etc. So frequency of gainers will be increased as a result of mutagenesis. We have expected losers, phenylalanine, cysteine, valine, etc. They should disappear as a result of mutagenesis. And what is good, we can test it. So let's test this hypothesis with cancer data first. So we take the biggest collection of cancer mutations, and let's concentrate on one example, from valine to alanine. So I will remind you that from valine to alanine, we go according to this trajectory of mutagenesis. And we just count. So we observed 78 mutations in the biggest collection of this human cancer mutations. From valine to alanine, 78, and backward from alanine to valine, 27. After, I just want to explain, but if we normalize, effect will be even stronger, so it works. And now we just do the same, but so all cancer data we visualize like this. So different types of substitutions here. So valine to alanine here. Dotted line is our null, so it's odds ratio plus 1. And we see valine to alanine, okay, so it's shifted on the right. And all amino acid pairs shifted on the right. And they really follow our butterfly scheme because there is no selection in cancer, because mitochondria is not really important. And the majority of non-selective mutations, they accumulate as if they are neutral. And so this is just proof of principle. Okay, butterfly scheme works on cancers. Now let's add a little bit of selection. Let's go to pathogenic database, MitoMap. So we analyzed 300 non-synonymous pathogenic substitutions. They are here. Okay, so number is not so big. We have huge standard deviation, but again, majority of dots, they shifted on the right. So majority of amino acid substitutions, they follow our hypothesis. So valine to alanine, here, our example. Okay, let's add more selection. Let's go to 100,000 complete genomes of human. We reconstructed pedigree, we reconstructed each mutation on each branch, and we counted all amino acid substitutions. And we see this one. So it's a way, we add more and more selection. So some amino acids, they behave not nicely according to our hypothesis, they against our hypothesis, but majority of them still shifted on the right, and our example, valine to alanine, is here. So it's significantly shifted. From valine to alanine, more common as compared to backward mutation. So it works. And now we want to extend it even more. We say, what happened in thousands, million years of evolution? Probably in mitochondrial genome, we expect that gainers, so all these gainers, will be more common, and losers on the periphery will be more and more rare. And now we can go to thousands of species with complete mitochondrial genome, and we count fraction of gainers, fraction of losers in mitochondrial genome, and plot it. Okay, and we did it. So here are birds, mammals, reptilia, amphibia, fishes, invertebrates, plants, fungi, and we decided to add bacteria, alpha-proteobacteria, as approximate relatives of mitochondria. And what we can see, so red is fraction of gainers, and gray fraction of losers. And we can see that in all vertebrates here, so frequency of gainers in all mitochondrial protein coding genes is much higher as compared to losers. So it's in line with our hypothesis. But now when we go left, maybe you don't see well, so gray goes up, so losers, they become more and more common. For example, in invertebrates, there is a shift. Losers here, gainers here, and losers, they become even more common in plants, fungi, and very common in mitochondrial ancestors. And gainers, they behave like this. They increase in frequency. And so, now we can interpret this that if this is really ancient mitochondrial genome, let's assume this. So origin of mitochondria was here, and the origin of asymmetrical mutational spectrum was here. So this rule C to T, A to G, it started at this moment of evolution. And so losers, they start to decrease, and gainers, they start to increase. So there is this big cross in evolution, which is formed in billions of years. And now you can ask why all vertebrates on the right, and invertebrates here, fungi here, bacteria here. But because we sorted them according to effective population size. So let's say vertebrates, they are rare enough, and there is this huge genetic drift here, and any suboptimal, slightly deleterious variance can be fixed because of random factor, because of genetic drift. And when we go left, invertebrates, they are much more, let's say, numerous as compared to vertebrates. So genetic drift is less powerful, selection is more deterministic. And we go left, plants, fungi, and bacteria, they're huge populations, very strong selection. Genetic drift is very weak. So when we go from left to right, just strength of selection is decreasing, and that's why we believe that frequency of gainers is increasing, and frequency of losers is decreasing as we assume with our butterfly scheme. So finally, we think that even if we believe that mitochondrial proteome, mitochondrial genes, they're very constrained, yes, they're constrained, but sometimes they're constrained not because of functional selection, but sometimes they're like mutational cold spots. Again, if it's gainer, there is no way to evolve from gainer. So already phenylalanine, that's dead end from the point of view for mitochondrial mutational spectrum. So if we're analyzing multiple alignment of mitochondrial proteins, and we see that some regions are super constrained, we can have a look carefully, and if 90% of amino acid gainers, it doesn't mean that they're really functionally important. It's just cold spot of mutagenesis. It's just dead end of this butterfly scheme. Okay, and my slide that now should we reanalyze all papers about positive selection mitochondrial genome? Because now we say that null hypothesis that there is butterfly scheme. And we just read carefully 3 papers, killer whale, European anchovy, another paper, and we say all substitutions alanine to threonine here, it's in line with our hypothesis, valine to methionine here, cysteine is more common in short-lived mammals. Yeah, because cysteine is loser and it disappears faster in rare populations of long-lived mammals because there is huge genetic drift in long-lived mammals. That's why they have no cysteine. And of course, cysteine predicts animal lifespan, but it's not positive selection. Okay, so my both take-home messages. First, mitochondrial mutational spectrum is informative, so we can decode it. And this is last take-home message, yes, that amino acids follow the same trend. Thank you very much.
Thank you very much. One question, guys.
Hi, it's here. So the question is, if the comparison that you make in the species is just restricted to the electron transfer genes that are encoded, or is just the whole genome?
So for majority of analysis, we use only 13 protein-coding genes which are coded in mitochondria, and when we compared with bacteria, we took only 10 high-quality orthologs. So, and we didn't take into account ND6 because it's an opposite trend.
Okay, and finally, I don't think that is adequate to think that plants or insects are less evolved than mammals or vertebrates, so...
But from point of view of effective population size, they are different.
Yeah, different, yes, but the evolution time is exactly the same. So the pressures would be the same.
Yes, but let's say, as a result of effective population size, we can assume that probability of fixation of slightly deleterious variants will be different. I will happy to discuss it. Thank you.
Thank you very much, Konstantin, very much. Thank you all the amazing speakers.